VBB provides the base current which controls the transistor to operate as a switch or a current amplifier. Practically, IB is provided by a potential divider circuit, and the whole biasing circuit only requires one power supply VCC. In the following few slides, we will discuss how to use R1 and R2 to bias a transistor in different operation regions. Let's start with the cutoff region. To do so, we have to ensure that the base current is equal to 0 and the base emitter PN junction does not conduct. In order to determine whether this transistor turns off, let's have some recapitulation about PN junction diode. We have learned that in order to determine whether a diode conducts, we remove the diode from the circuit and calculate the potential difference VD. If VD is smaller than 0.7 volt, it is too weak to overcome the potential barrier in the PN junction. Therefore, when the diode is connected back to the circuit, the diode current will be 0. For your revision, more details are listed here, which can also be found in the resources at the top right corner. Now, we apply the same technique to the transistor. Firstly, disconnect it from the circuit. After that, we calculate VBE by applying potential divider formula. If this value is less than 0.7 volt, then VBE must be less than 0.7 volt. In such case, what will happen when the transistor is connected back to the circuit? Will the base emitter PN junction conduct? Since VBE is less than 0.7 volt when the transistor is disconnected from the circuit, the base emitter junction will not conduct when the transistor is connected back to the circuit. Therefore, IB is equal to 0 and the transistor operates in the cutoff region. When the base current is equal to 0, the collector current is approximately equal to 0, and the voltage difference across the collector and the emitter is approximately equal to VCC. The base current can be increased by adjusting R1 and R2. If the base current is increased to 50 microamperes, the Q point will shift up along the low line, and the collector current will be 10 milliamperes. If the base current is increased to 100 microamperes, the collector current will increase proportionally to 20 milliamperes. It can be calculated by this formula. IC is equal to beta times IB, where beta is the DC current gain of the transistor. It is given as 200. For the base current of 100 microamperes, IC is equal to 20 milliamperes. And if the base current is increased to 150 microamperes, the collector current will increase proportionally to 30 milliamperes, which can be calculated by the same formula.